Students, so today we will have our last lecture on the chapter on the structure of materials. And our today's lecture is on the characterization of crystal structure. So after talking about a lot of knowledge on crystal structure, the natural question is how you can characterize those crystal structures. As a matter of fact, the characterization of crystal structure starts from the discovery of X-ray by this scientist Röntgen in the late 19th century. So the reason why X-ray can interact with crystal structure is because the wavelength of X-ray is on the same order of magnitude as the atomic radius. So that's the reason why they can interact with each other strongly, so that you can get information from your X-ray characterization on the crystal structure. So to discuss the principles of X-ray matter diffraction or interaction, we will first need to have some basic knowledge on the interference of electromagnetic waves. So you probably learned this in your college physics class or even your high school physics class. And suppose you have two waves. So this is your first wave, this is your second wave. And depending on the phase of these two waves, if these two waves have exactly the same phase or zero difference in their phases, they will become so-called coherent waves. And when they are combined together, they will generate this so-called constructive interference. And the magnitude or the amplitude of the wave will be doubled. So this is so-called coherent waves and constructive interference. But in general, there will be phase difference in these two waves. And in that case, these two waves are so-called incoherent waves. And the special case is the destructive interference, where the two waves have exactly opposite phase, or essentially 180-degree phase difference. So when these two waves are combined together, they will just cancel each other and result in nothing. So these are called destructive interference. So, and then the crystal structure we are interested in to talk about the matter X-ray interaction is the interplanar crystal spacing. So suppose you have a set of parallel planes of items, and the planes have Miller indices of HKL. And then we can easily calculate the distance or the interspacing between neighboring parallel planes by this equation, where the interplane spacing d can be calculated by the lattice constant divided by the square root of h squared, k squared, and l squared. So about 100 years ago, the British scientists, father and son, Henry Bragg and Lawrence Bragg, they developed the principles of X-ray matter interactions. So suppose you have a set of parallel atomic planes, and you have these parallel incoming electromagnetic waves with a wavelength of lambda. Then the condition for the constructive interference is the so-called Bragg's diffraction law, where an integer number of your wavelength should equal to 2 times the interspacing of your parallel planes times the sine theta. Theta is the angle between your incoming electromagnetic wave and your parallel atomic planes. So this is the famous Bragg diffraction law. So essentially, in nowadays, you can have such modern so-called X-ray diffraction machine where you just measure the conditions for the Bragg diffraction laws and determine the crystal structure of your sample. So in particular, if you put your sample here and you are shining a parallel rays of electromagnetic wave, or essentially here is the X-rays to the sample, and the X-ray will be diffracted. And there will be a detector on the other side of the machine. And then you do an automatic scan by changing this incoming angle theta. And you get a full range of spectrum as a function of your theta values. And the spectrum you will obtain is something like this. So this is your diffraction angle to theta on the horizontal axis, and the vertical axis is the diffraction magnitude. You have peaks at positions of constructive interference, or which means you have certain atomic planes there. So essentially, with these X-ray diffraction spectrums, you can determine the interspacing of parallel atomic planes at these particular angles. And then with some database on crystal structure, you can determine the actual structure of your crystal. And if you have an amorphous structure, instead of having these clearly defined peaks, you will have a relatively broad bump of your X-ray diffraction pattern. And this bump is characteristic for amorphous materials. An alternative way to do this diffraction experiment is to use the transmission electron microscope, or TEM, where you have, suppose you have your sample here, and you have a few parallel set of high energy electron beams transmitting across the sample. And after all these complex magnetic lenses, you will have a detector plane on the bottom where you can, similar to your X-ray diffraction experiments, you can have diffraction spots or patterns there which can be used to determine your actual crystal structure. So the actual wavelengths of your electrons or electron beams really depend on the energy of your acceleration of electrons. So here are some typical values for the wavelengths used in X-ray diffraction and on TEM diffraction, or electron beam diffraction. And you can also use neutron, accelerating the neutrons to high energies and give a particular wavelengths. So here I just show an example of an TEM image and the corresponding electron diffraction analysis. So here I show a sample of aluminum magnesium silicon alloy, where you can see a lot of tiny precipitates in the alloy. And if you just do diffraction on these precipitates, you will generate such electron diffraction spots. And each of these spots will correspond to one set of parallel atomic planes. And using these diffraction pattern in TEM, you can determine the actual crystal structure of your crystal. So in general, if you have a crystal under TEM, electron beam diffraction will give individual diffraction spots that corresponding to particular parallel atomic planes. And instead, if you have amorphous material, for example, if you are doing TEM electron diffraction on glass, you generate circular continuous rings instead of these individual diffraction spots. And such rings is characteristic of amorphous structure. So in today's lecture, we have talked about the characterization of crystal structures using diffraction techniques. Thank you very much.